In the quiet glow of a universe that never truly sleeps, light does something strange. It races across the cosmos with perfect consistency, never slowing, never speeding up, always arriving with the same unyielding pace. No matter where it comes from, no matter who is watching, and no matter how fast the observer is already moving, this is not a suggestion, it is not a habit, it is a rule written into reality itself. Light has no mass, nothing is pushing it forward, nothing is weighing it down, and yet it cannot go any faster than it already does, not even by the smallest amount. Scientists have tested this limit again and again, across decades, across galaxies, across every experiment clever enough to challenge it. Each time, the universe answers with the same quiet certainty. This speed is not about light trying its hardest. It is not about resistance, friction, or exhaustion. It is something deeper, something built into space and time themselves. Tonight, this journey moves slowly through that mystery, through the nature of motion, the strange behaviour of time, and the hidden structure of spacetime that decides how fast anything is allowed to be. No equations, no rushing, just a calm unfolding of why the fastest thing in the universe is not fast because it has to be, but because reality leaves it no other choice. If you enjoy drifting through the deeper rules that shape existence, consider subscribing to continue these quiet explorations. For now, settle in. Let the universe move at its own pace. Speed feels like one of the most flexible ideas in everyday life. Press a little harder on the accelerator and a car responds. Add more power to an engine and it spins faster. Run downhill instead of uphill, and motion becomes easier, quicker, almost effortless. Speed feels negotiable, something that can always be increased with the right conditions. At first glance, it seems natural to assume the universe works the same way. Yet, hidden beneath all motion, from drifting galaxies to flickering atoms, there exists a very different rule, a universal speed limit. Not a guideline, not a suggestion, but a deep structural feature of reality itself. This limit is not posted on signs or enforced by anything visible. It emerges quietly from the way space, time, and motion are woven together. What makes this idea remarkable is not just that a limit exists, but that it appears everywhere. It shows up in astronomy, in particle physics, in the behaviour of energy, and even in how cause and effect remain ordered. Wherever careful measurements are made, the same boundary appears, steady and unavoidable. It is tempting to think of this limit as a rule imposed on light. Light is fast, dramatic, and easy to point to, so it often becomes the focus. But the deeper truth is that light is not being restricted. Light is revealing something far more fundamental. The limit does not belong to light alone. It belongs to the universe. To understand this, it helps to contrast cosmic motion with familiar speed limits. A speed limit on a road exists for practical reasons. It can be changed, it can be broken. It depends on safety, environment, and human judgment. If technology improves, the limit might rise. If conditions worsen, it might fall. These limits are external rules placed on motion. The cosmic speed limit is nothing like that. There is no faster lane beyond it. No special condition under which it can be lifted. No hidden shortcut that clever engineering might uncover. The limit is not added to motion from the outside. It is built into how motion itself is defined. Speed, at its core, is a relationship between distance and time. How far something moves and how long that movement takes. In everyday life, distance and time feel fixed and independent. A meter is a meter. A second is a second. Speed changes because motion changes. In the universe, distance and time are not independent in the way intuition expects. They are part of a single structure often called spacetime, a framework that links where events happen to when they happen. Motion is not simply movement through space, it is movement through spacetime, with space and time sharing the work. This is where the cosmic speed limit enters naturally. There exists a maximum pace at which events can be connected through spacetime, a maximum rate at which information, influence, or cause can travel from one place to another. This pace is the same everywhere, regardless of direction, location, or the motion of the observer making the measurement. This universality is crucial. If the limit varied from place to place, the universe would lose coherence. Events could unfold differently depending on location. Communication would become unreliable. Physical laws would fracture. Instead, the same boundary appears wherever measurements are made, tying the universe together into a single, consistent whole. Importantly, this limit does not only constrain light, it constrains everything that can transmit information. Signals, forces, interactions, and changes of any kind must respect it. Light simply happens to travel at this maximum pace, which is why it so clearly reveals the limit's existence. Objects with mass behave differently, not because they are being restricted, but because their motion must be divided between space and time. They always retain some motion through time, which gives them rest frames, aging, and flexibility and speed. As they are given more energy, they move faster through space. But spacetime responds by adjusting time and distance in a way that prevents them from ever reaching the boundary light occupies. This response is not guessed, it is observed. Particle accelerators push particles to extraordinary energies, yet those particles never cross the universal limit. Instead, added energy goes into increasing inertia, altering how time passes for the particle, and changing how distances appear along its direction of motion. Speed increases slow down and eventually taper, not because something resists motion, but because space-time itself redistributes what motion means. The same structure preserves cause and effect. If influences could travel faster than the cosmic limit, events could arrive before their causes. Effects could precede actions. Different observers would disagree not just about measurements, but about what happened first. The universe avoids this quietly, by ensuring that information never outruns the boundary that spacetime defines. In this sense, the cosmic speed limit is not a constraint that restricts reality. It is a safeguard that keeps reality intelligible. It ensures that nearby events influence each other before distant ones do. It allows signals to propagate outward in layers rather than appearing everywhere at once. It gives time a direction and events an order. Without this limit, explanation itself would become unreliable. What is striking is how little drama accompanies all of this. There is no cosmic enforcement mechanism, no special force that intervenes when things approach the limit. The geometry of spacetime simply does not offer paths that exceed it. Motion remains free within the structure that gives motion meaning. This makes the limit feel less like a wall and more like a contour, a natural shape that everything follows without resistance. Once this perspective settles in, the idea of a universal speed limit becomes less surprising and more inevitable. A universe that supports structure, complexity, and understanding must allow influence to spread, but not infinitely fast. It must balance connection with order. The cosmic speed limit is how that balance is achieved. Light does not race toward the limit. It lives on it. Everything else moves within it. And from that quiet relationship emerges the stability of stars, the predictability of physics, the reliability of cause and effect, and the steady unfolding of time itself. The limit is not a punishment for motion. It is the rhythm that allows motion to make sense. Meeting the cosmic speed limit, then, is not about discovering what cannot be done. It's about recognizing the shape of possibility itself, written into the structure of the universe, steady, universal, and quietly holding everything together as it moves. In everyday life, speed feels wonderfully straightforward. It is distance divided by time, a simple idea learned early and rarely questioned. A walk takes longer than a drive. A train outruns a bicycle. A thrown ball slows as it climbs and speeds up as it falls. Speed feels like something objects possess, something that can be adjusted by effort, terrain, or machinery. This intuition works beautifully at human scales, which is why it feels so reliable. When a journey is planned, the mind imagines distance first and time second. How far is the destination? How long will it take to get there? Speed becomes a convenient summary, a single number that links the two. Faster means less time. Slower means more. Nothing about this picture feels mysterious. The universe, however, is under no obligation to preserve intuition beyond the conditions that created it. As speeds increase and distances stretch beyond everyday experience, the simple picture begins to fray. At very high velocities, familiar rules stop behaving the way the mind expects. Objects no longer agree on how long a journey takes. Distances no longer mean the same thing to everyone measuring them. Clocks stop ticking in unison. What once felt fixed becomes flexible. This is not because speed itself changes its meaning arbitrarily, but because the ingredients used to define speed are not as independent as they appear. Distance and time feel separate because daily life unfolds in a narrow range of conditions. Motion is slow compared to the cosmic limit. Gravity is weak. Differences in perspective are small. Under these conditions, space behaves like a rigid stage and time flows evenly for everyone involved. Speed then feels like a property of objects moving across that stage. At extreme speeds, this picture quietly collapses. Speed is not something measured in isolation. It is always inferred from two measurements taken together, a length and a duration, a ruler and a clock. Change either one, and speed changes even if the motion itself does not. At low speeds, rulers and clocks agree closely enough that the distinction hardly matters. At high speeds, the distinction becomes unavoidable. This is where the universe reveals a deeper rule. Space and time are not separate arenas stitched together for convenience. They are aspects of a single structure. Motion does not take place through space alone or through time alone, but through both at once. Every moving object traces a path that blends distance with duration. That blended path is what physicists refer to as spacetime, though the name itself is less important than the idea behind it. Imagine a journey described not just by where it goes, but by when it arrives. Each step forward through space is also a step forward through time. Objects cannot pause their movement through time any more than they can pause existence itself. Even when standing still, something is still moving through time at a steady pace. This shared motion has consequences. When an object moves faster through space, something else must give. The universe does not allow total motion to increase without adjustment. Instead, motion through space and motion through time trade with one another. As speed through space increases, the rate at which time passes for that object changes. Distances along the direction of motion also adjust. These changes are not corrections applied afterward. They are part of how spacetime maintains consistency. This is why everyday intuition breaks down. Intuition assumes that time ticks the same way for everyone, and that distances remain fixed regardless of motion. At extreme speeds, neither assumption holds. Speed itself remains meaningful, but its measurement depends on the observer's state of motion, their reference frame, and the clocks and rulers they carry with them. A useful metaphor is a long journey taken with a single clock. Two travellers may leave together and arrive together, yet experience different amounts of time along the way. One may have taken a winding route, another a straighter one. The destination is the same, but the paths differ. In spacetime, motion works in a similar fashion. Different paths through the same events can involve different mixtures of space and time. This does not make speed subjective in a chaotic way, it makes it relational. Speed is always measured relative to an observer. There is no universal vantage point from which all motion can be judged absolutely. Each observer carries their own coordinate system, their own way of slicing space-time into moments and distances. At low speeds, these slices align so closely that the differences vanish into the background. At high speeds, the differences matter. This prepares the ground for understanding why a universal speed limit can exist at all. If speed were only about crossing space, then nothing would prevent endless acceleration. But because speed involves space and time together, and because space-time itself has structure, there emerges a natural boundary, a maximum rate at which events can be connected, measured consistently by all observers regardless of their motion. Light travels at that rate, not because it is exceptional in character, but because it follows the deepest pathways space-time allows. Other objects carrying mass cannot fully shift their motion into space without losing their motion through time. The geometry prevents them from reaching the same pace. This interplay also explains why clocks behave strangely at high speeds. A moving clock ticks more slowly relative to a stationary observer, not because it is malfunctioning, but because it is taking a different path through space-time. More of its motion is devoted to space, leaving less available for time. The clock remains perfectly normal in its own frame. It is the comparison that reveals the difference. Distance behaves similarly. Lengths along the direction of motion contract not because objects are being compressed, but because space-time itself is being sliced differently by observers in motion relative to one another. Measurements remain internally consistent even when they disagree across frames. Seen this way, speed becomes less about raw motion and more about perspective. It is not an intrinsic trait of an object, like colour or mass. It is a relationship between an object's path and the space-time structure in which that path is traced. Everyday intuition fails because it was never designed to handle this level of subtlety. It evolved to navigate walking speeds, short distances, and weak gravitational fields. The universe operates far beyond those conditions, and when it does, it reveals rules that feel strange only because they were hidden before. The idea of space-time does not need to be formalized to be felt. It appears naturally when thinking carefully about journeys, clocks and distances. Every trip has a duration, every movement has a location, every speed depends on both. The universe simply refuses to let these elements be separated when motion becomes extreme. Understanding this does not make motion feel more complicated. It makes it feel more unified. Speed is no longer just how far something goes. It is how an object moves through the combined fabric of space and time. The cosmic speed limit emerges from that fabric naturally, not as a restriction imposed afterward, but as a feature that preserves consistency across all perspectives. Once this is understood, later surprises lose their sharpness. The strange behaviour of clocks, rulers, and fast-moving objects begins to feel less like a violation of common sense, and more like an extension of it. Everyday intuition is not wrong. It is simply incomplete. The universe does not abandon simplicity. It deepens it. Speed still means distance over time. Journeys still take time. Clocks still tick. What changes is the realization that distance and time are partners, not strangers, and that motion always involves both, whether or not intuition has noticed. With that realization in place, the idea of a universal speed limit stops feeling arbitrary. It becomes an expression of how space-time keeps motion coherent, measurements consistent, and reality shared, even when speeds climb far beyond anything daily life ever encounters. Mass is one of those ideas that feels obvious until it is examined more closely. In everyday life, mass is associated with heaviness, with how difficult something is to lift, push, or slow down. A heavy object resists motion. A light object moves more easily. The connection feels intuitive, reinforced by constant experience with gravity and effort. But mass is doing more than making things heavy. At its core, mass is a measure of how strongly an object resists changes to its motion and how it responds to the structure of space-time. An object with mass carries inertia. It prefers to keep doing what it is already doing, whether that is resting or moving at a steady pace. It also interacts with gravity, contributing to the curvature of space-time and responding to that curvature in return. This resistance to change is subtle but profound. Push on a massive object and it responds gradually. Give it energy and its motion changes, but never instantly. Mass ties objects to time. It gives them rest frames, internal clocks, and histories that unfold moment by moment. Light does not share this property. Light has no rest mass. This is not a poetic statement or a convenient approximation. It is a precise physical fact confirmed by countless experiments. There is no frame of reference in which light can be brought to rest and weighed. No perspective exists where a photon sits still long enough to be assigned mass in the usual sense. This absence often leads to a tempting assumption. If mass causes resistance, then no mass must mean no resistance. If mass creates limits, then masslessness must mean freedom. Light, then, should be able to move however it likes, unconstrained and unrestricted. The universe does not work that way. Having no mass does not mean having no rules. It means playing by a different relationship with space-time. To understand why, it helps to revisit what mass allows in the first place. Objects with mass can always find a reference frame in which they are at rest. Sit alongside them, move with them, and they become still relative to you. This is true no matter how fast they are moving, as long as their speed remains below the cosmic limit. That possibility of rest is crucial. It allows massive objects to experience time internally, to age, to measure duration with clocks carried along their paths. Light has no such option. There is no reference frame in which light is at rest, no way to move alongside it and share its perspective. This is not a limitation imposed by technology or imagination. It is a consequence of how space-time is structured. Motion through space-time always involves a combination of space and time, but light occupies a special boundary where that combination reaches an extreme. For objects with mass, motion can be redistributed. Speed up through space, and time adjusts. Slow down through space, and time flows more freely. This trade is what allows massive objects to approach the cosmic speed limit without ever reaching it. Space-time reshapes their experience gently, preserving consistency. Light has no room for that trade. Because light has no rest mass, it cannot slow down and still exist as light. Slowing would require a rest frame, and a rest frame does not exist for massless particles. Light is not racing toward the speed limit. It is born at it. From the moment it exists, it moves along the fastest paths space-time allows. This is where the idea of freedom quietly reverses. Massless does not mean unconstrained. It means fully constrained by geometry. Light follows what are known as null paths through space-time, routes where distance and time are balanced in a precise way. Along these paths, there is no passage of proper time. From the perspective of space-time itself, light does not age, linger, or pause. It connects events directly, tracing the boundary between what can influence what. This makes light exquisitely sensitive to the structure of space-time. It responds instantly to curvature. It bends near massive objects. It follows the geometry exactly, without inertia to soften or delay its response. Where space-time curves, light curves with it. That responsiveness is sometimes mistaken for freedom, but it is closer to obedience. Light does not choose its path. It follows the geometry completely. This explains why adding energy to light does not change its speed. For massive objects, energy can be added in ways that alter motion gradually. More energy usually means more speed. For light, energy changes something else entirely. It changes frequency, colour, and momentum, but not pace. The speed is fixed because there is nowhere else for light to go within spacetime structure. The absence of mass removes flexibility rather than adding it. This also helps resolve a common confusion about weightlessness. Astronauts floating in orbit feel weightless, yet they still have mass. They resist being pushed, they carry clocks, they age. Weightlessness is not the absence of mass. It is the absence of support forces. Mass remains, quietly governing how motion unfolds. Light goes further, it has neither weight nor rest mass, and because of that, it lacks the options that massive objects take for granted. It cannot slow down, it cannot stop, it cannot experience time internally. It exists entirely as motion. This makes light a boundary case, not an exception. It marks the edge of what motion can mean. The rules governing light are not separate from the rules governing everything else. They are the same rules, taken to their limit. Mass allows motion to be distributed between space and time. No mass removes that flexibility, forcing motion to align perfectly with spacetime's fastest connections. Seen this way, the behaviour of a light stops feeling strange. It becomes inevitable. Light behaves differently because it occupies a different relationship with spacetime, not because it escapes the rules. In fact, it obeys them more completely than anything else. It traces the structure exactly, revealing the shape of reality without distortion. This is why light plays such a central role in physics. It is not just fast, it is informative. By observing how light moves, bends, and arrives, scientists learn about spacetime itself. Light acts as a probe, mapping geometry by following it faithfully. The absence of rest mass is what makes this possible. If light had mass, it would have inertia, it would resist curvature, it would lag behind geometry instead of revealing it. The universe would become harder to read. By having no rest mass, light becomes the clearest messenger spacetime can provide. This also builds curiosity around other massless or nearly massless phenomena. Fields, waves, and interactions that move at or near the cosmic speed limit reveal something about the structure they inhabit. They show where flexibility ends and definition begins. Massless does not mean free. It means precise. It means bound tightly to geometry, to order, and to the deepest structure of spacetime. Light is not escaping constraints. It is living at the edge of them, tracing a path that cannot be altered without altering reality itself. Understanding this prepares the ground for the next step. If light has no mass and no rest frame, if it always moves at the same pace, then questions naturally arise about energy, time, and why pushing harder stops producing more speed. Those questions do not arise because light is strange. They arise because light reveals where the familiar rules of motion reach their limit. In that revelation, light does not break the universe's logic. It completes it. In everyday experience, adding energy produces a very familiar result. Push harder, and something moves faster. Pedal more strongly, and the bicycle accelerates. Burn more fuel, and an engine delivers more speed. This pattern is so reliable that it becomes an expectation. Energy in, speed up. The relationship feels direct, almost mechanical, and for most of daily life it works exactly as expected. For objects moving slowly compared to the cosmic speed limit, this intuition is remarkably accurate. Add energy to a ball, and it rolls faster. Add energy to a car and it accelerates down the road. Even add energy to a spacecraft and its velocity steadily increases. Nothing about this behaviour hints that there might be a ceiling waiting ahead. But as motion begins to approach the universe's deepest boundary, something subtle changes. At higher and higher speeds, each additional burst of energy produces less and less increase in velocity. The object still responds, it still accelerates, but the acceleration tapers. The speed climbs more slowly, as if the universe were quietly redirecting the effort somewhere else. No matter how much energy is added, the speed never quite reaches the same pace that light travels. This is not a theoretical curiosity, it is observed directly. Particle accelerators provide a clear example. These machines feed enormous amounts of energy into tiny particles, pushing them closer and closer to the cosmic speed limit. Early on, the particles accelerate rapidly. But as their speed increases, something unexpected happens. Vast increases in energy produce only tiny changes in velocity. The particles get more energetic, but not much faster. Importantly, nothing breaks. No resistance appears. No mysterious force pushes back. The machinery works exactly as designed. The particles simply refuse to cross the boundary. The key insight is that energy does not only go into speed. At low velocities, most added energy shows up as increased motion through space. Speed rises, momentum grows, and everything behaves as intuition predicts. At extreme velocities, energy begins to flow into other aspects of motion, aspects that are easy to overlook when speed is the only thing being measured. One of those aspects is inertia. As an object moves faster, it becomes increasingly resistant to changes in its state of motion. Not because its mass is increasing in a literal sense, but because space-time itself is responding. The object's energy contributes to how strongly it resists further acceleration. Each additional push has less effect on speed and more effect on how difficult it becomes to change that speed at all. Another place energy goes is into altering how time passes for the moving object. As speed increases, time slows relative to an outside observer. Internal processes unfold more gradually. Clocks tick more slowly. This is not an illusion and not a malfunction. It is a real, measurable change in how space-time is experienced along the object's path. Distance changes as well. Lengths along the direction of motion contract relative to an outside frame. Again, nothing is being crushed or compressed. Space-time itself is being sliced differently by observers in different states of motion. Measurements remain consistent within each reference frame, even when they disagree across frames. All of these adjustments happen together. As more energy is added, space-time redistributes how motion is expressed. Less of that motion can appear as increased speed through space. More of it appears as increased inertia, altered time flow, and changed spatial measurements. Speed stops being the primary place energy can go. This redistribution is not chosen. It is enforced by the structure of space-time. There exists a maximum rate at which events can be connected through space-time. Approaching that rate does not feel like hitting a wall. It feels like diminishing returns. Each additional unit of energy produces less visible change in velocity, because the geometry has fewer available directions in which motion can be expressed. A useful way to picture this is to imagine pouring water into a container that gradually narrows. At first, the water level rises quickly. As the container narrows, each additional pour raises the level less than before. The water is still being added. It is simply being distributed into a smaller and smaller available space. Speed behaves in a similar way near the cosmic limit. This behaviour is sometimes described as energy being converted into mass, but that language can be misleading. Nothing material is being created. What is changing is how energy contributes to motion and inertia within space-time. The object becomes harder to accelerate, not heavier in the everyday sense, but more deeply embedded in the geometry it is moving through. Crucially, this effect is not guessed based on theory alone. It is measured, tested, and confirmed. Accelerators observe it. Precision clocks confirm the associated time effects. Length measurements agree with the predicted contractions. Independent experiments converge on the same conclusion. Adding energy never pushes an object past the boundary. Light occupies. Light itself highlights the contrast. Light does not speed up when energy is added. Instead, its energy changes frequency and wavelength. Color shifts, intensity increases, but pace remains fixed. Light has no option to redistribute energy into slower time or increased inertia, because it has no rest frame. It already occupies the boundary. All additional energy must express itself in other ways. Massive objects, by contrast, begin by behaving like everyday intuition expects, and then gradually transition into this different regime as speed increases. The closer they get to the cosmic limit, the more their behaviour begins to resemble light's rigidity, though they never fully reach it. This smooth transition is important. There is no sudden threshold, no sharp break where classical intuition abruptly fails. Instead, intuition becomes less accurate little by little as conditions move further from the ones it evolved to handle. The universe does not forbid high speeds. It simply redefines what speed means as limits are approached. This redefinition preserves order. If energy could always be converted directly into speed, then faster than light motion would be possible in principle. That would allow signals to outrun causality, effects to precede causes, and different observers to disagree about the sequence of events. By redirecting energy into other aspects of motion, spacetime quietly prevents this outcome. Once again, the universe avoids drama. There is no enforcement mechanism, no warning signal, just geometry doing its work. The paths that would correspond to faster than light motion do not exist for massive objects. As energy increases, spacetime responds by changing how motion is expressed, rather than allowing speed to exceed the boundary. This also explains why phrases like infinite energy are sometimes used when discussing the cosmic speed limit. To push a massive object all the way to the boundary would require endlessly adding energy, because each addition produces ever smaller changes in speed. The limit is not unreachable because of a force. It is unreachable because of diminishing returns built into the structure itself. Seen this way, adding energy never truly stops working. It simply stops doing what intuition expects. Energy continues to matter. It increases inertia. It deepens time effects. It alters how space-time is experienced along the object's path. What it no longer does, once speeds are extreme enough, is translate efficiently into more velocity. This understanding reshapes the original expectation. The universe is not saying no to acceleration. It is saying yes to consistency. It allows energy to change motion in every way except the one that would break the shared structure of space-time. When viewed through this lens, the cosmic speed limit feels less like a barrier and more like a guiding principle. It channels energy into forms that preserve coherence, causality, and order. Objects can become extraordinarily energetic without tearing the universe's logic apart. Adding energy does not fail, it is redirected. And in that redirection, the universe reveals a quiet sophistication. Motion is not just about going faster. It is about how space and time cooperate to keep reality stable, predictable, and shared, even when pushed to its most extreme edges. Time feels like the most reliable feature of experience. It moves forward steadily, second by second, carrying moments along with it. A minute lasts a minute, an hour lasts an hour. Two clocks placed side by side tick in agreement, and nothing in ordinary life suggests that this agreement could ever fail. Time feels universal, shared, and absolute. That sense of certainty begins to soften when speed enters the picture. At low velocities, time behaves exactly as intuition expects. A journey takes longer if the distance is greater. Two travellers who leave together and arrive together agree on how much time has passed. Speed changes how quickly a destination is reached, but not how time itself flows. Time feels like a background rhythm, unaffected by motion. As speeds increase, however, something quietly remarkable happens. Time itself begins to change. This is not a metaphor and not a trick of perception. It is a physical effect that has been measured, tested, and confirmed. As an object moves faster through space, time passes more slowly for that object compared to an observer who is moving more slowly. The faster the motion, the greater the effect. Time stretches, not everywhere, but along the path of the moving object. At first this sounds impossible. How could time slow down? How could two clocks disagree if they were both built correctly? The confusion comes from assuming that time is something external, flowing identically for everyone regardless of motion. That assumption works at everyday speeds, but it is not how the universe actually operates. Time is not independent of motion. It is part of space-time. Every object moves through space-time, not just through space. Even when standing still, something is still moving forward through time at a steady pace. Motion through space and motion through time are linked. Change one, and the other adjust in response. A simple way to imagine this is to think of a journey that must always maintain a fixed overall pace. Some of that pace can be spent moving across space. The rest must be spent moving through time. If more of the journey is devoted to space, less remains available for time. The total does not change, but the distribution does. This redistribution is what causes time dilation. Consider a clock travelling on a fast-moving spacecraft. From the perspective of someone watching from Earth, that clock ticks more slowly, seconds stretch, minutes take longer to pass. From the perspective of the traveller, however, nothing feels unusual. Their clock ticks normally, their heartbeat remains steady. Their thoughts unfold as usual. Time has not changed for them locally. It has changed relative to someone moving differently. This is a crucial point. Time dilation is not something a traveller experiences as a slowing sensation. It is something revealed when different reference frames compare measurements. Each observer's experience is internally consistent. The difference emerges only when paths through space-time are compared. This effect is not speculative. It has been measured using precision clocks placed on fast-moving aircraft and satellites. Clocks that travel quickly tick more slowly than identical clocks that remain on the ground. The difference is small at everyday speeds, but it grows as speed increases. The universe does not hide this behaviour. It reveals it whenever measurements are careful enough. The reason time behaves this way is deeply connected to the cosmic speed limit. If time did not slow as speed increased, then adding enough energy would allow objects with mass to reach and exceed the boundary that light occupies. That would break the shared structure of space-time. Causes could outrun effects. Signals could arrive before they were sent. Different observers would disagree not just about measurements, but about the order of events. Time adjusts to prevent this. As an object moves faster through space, space-time compensates by slowing the flow of time along that object's path. This ensures that the object's total motion through space-time never exceeds the universal limit. Speed through space increases. Speed through time decreases. The balance is maintained automatically. This adjustment is not a patch or a correction added afterward. It is built into the geometry of space-time itself. A helpful thought experiment involves a simple clock made of light bouncing between two mirrors. Each tick corresponds to light travelling from one mirror to the other and back again. If the clock is at rest relative to an observer, the light moves straight up and down and the ticks occur at a steady rate. If the clock is moving sideways at high speed, the light must follow a longer diagonal path between the mirrors. The light still moves at the same pace, but the path is longer, so each tick takes more time. The clock runs slow. This is not because the clock is faulty, it is because the geometry of spacetime demands it. The light inside the clock must always travel at the same speed, regardless of the clock's motion. To preserve that rule, time stretches. This thought experiment captures the essence of time dilation without relying on equations. It shows that time does not slow arbitrarily. It slows in exactly the way needed to keep the speed of light constant in every reference frame. Light itself sits at the extreme of this behaviour. Because light always moves at the cosmic speed limit, it has no motion left to devote to time. Along the path of light, no proper time passes at all. From the perspective of spacetime, light does not experience duration. It connects events without aging between them. This is not something light perceives, because there is no frame in which light can make observations. But it is a meaningful statement about how light traces spacetime. For objects with mass, time never stops. It can slow dramatically as speed increases, but it never vanishes. This is why massive objects can age, carry clocks, and experience sequences of moments. Light cannot do these things because it exists entirely at the boundary where time no longer contributes. This difference reinforces why light always behaves differently from everything else. Time dilation also explains why journeys at extreme speeds produce surprising results. A traveller moving close to the cosmic speed limit can cross vast distances while experiencing very little time. To outside observers, the journey takes years or centuries. To the traveller, it may feel brief. Both perspectives are correct within their own reference frames. Spacetime allows both descriptions without contradiction. Once again, intuition struggles because it expects time to be universal. The universe instead offers something more flexible and more precise. Time adapts to motion in a way that preserves consistency across all observers. This adaptability is not chaotic, it is tightly constrained. Time slows by exactly the amount needed to maintain the speed limit and preserve causality. No more, no less. The calm elegance of this mechanism is easy to miss because it works so smoothly. There is no abrupt transition where time suddenly misbehaves. The effect grows gradually as speed increases. At low speeds it is negligible. At high speeds it becomes dominant. The same rule applies everywhere. Understanding this changes the way the cosmic speed limit is perceived. It is no longer just a cap on velocity. It is a principle that reshapes time itself. Space and time cooperate, trading roles to keep motion meaningful and shared. Time does not fail at high speeds, it adjusts, and in that adjustment the universe reveals a deep commitment to consistency. Rather than allowing motion to break structure, spacetime bends time just enough to keep everything aligned. Light remains the fastest messenger. Massive objects approach the boundary without crossing it. Cause and effect remain ordered. Time behaving strangely is not a flaw in reality. It is the sign that reality is doing exactly what it must to remain coherent. As this idea settles, time begins to feel less like a rigid river and more like a responsive dimension, one that stretches and adapts as motion demands. It flows differently along different paths, not to confuse, but to preserve the deeper rhythm that allows events to connect without contradiction. Light lives at one extreme of this rhythm, untouched by time entirely. Everything else moves within it, carried forward by moments that slow, stretch, and adjust, all in service of a universe that refuses to rush itself, even when motion pushes toward its ultimate limit. When motion becomes extreme, space itself begins to participate in ways that feel unfamiliar at first. In everyday life, distance feels fixed and dependable. A meter is a meter. A room has a definite length. Two people can agree on how far apart things are without difficulty. Space feels like a stable backdrop. Something motion happens within but never alters. That expectation holds beautifully at low speeds. As long as motion remains far below the cosmic speed limit, measurements of distance line up neatly between observers. Rulers agree, maps make sense, journeys feel predictable, space behaves as intuition expects, quietly waiting to be crossed. As speeds climb higher, however, that quiet agreement begins to loosen. When an object moves extremely fast relative to an observer, distances measured along the direction of motion begin to shrink. This effect is known as length contraction, though the name can be misleading if taken too literally. Objects are not being squeezed or compressed. Nothing physical is happening to the material itself. Instead, space is being measured differently by observers in different states of motion. This distinction matters. Length contraction is not a force acting on objects. It is a consequence of how spacetime is structured. Distance and time are not independent quantities that sit side by side. They are woven together, and when motion changes the balance between them, measurements of both must adjust to preserve consistency. To understand why, it helps to remember that speed is never measured using space alone. It always involves time as well. Measuring how far something stretches requires deciding which points are considered simultaneous. Measuring length is, at its heart, a timing problem. At everyday speeds, this subtlety can be ignored. Different observers agree closely enough on what counts as now that their measurements align. At extreme speeds, that agreement breaks down. Observers moving relative to one another no longer share the same slices of space-time. What one observer calls simultaneous, another does not. As a result, distances change. Imagine a long train moving past a platform at tremendous speed. Someone standing on the platform measures the length of the train by recording the positions of its front and back at the same moment. Someone riding inside the train measures its length using clocks and rulers that move with it. Both measurements are correct within their own reference frames, yet they do not agree. The train has not changed. Space has. This is where space joins the conversation alongside time. Earlier, time revealed its flexibility by slowing down as speed increased. Now, space reveals its own adaptability by shortening along the direction of motion. These two effects are not separate tricks. They are coordinated responses within spacetime. Together, they preserve the same fundamental rule. There exists a maximum pace at which events can be connected through spacetime, and that pace is the same for all observers. This pace corresponds to the speed of light, which is just under 300 million meters per second, or about 300,000 kilometers every second. This number is not arbitrary. It is the scale that defines how space and time trade with one another. When an object moves faster through space, spacetime compensates by altering both time and distance. Time slows, length contracts. These changes ensure that no observer ever measures anything exceeding that boundary. The speed limit is preserved not by resistance, but by geometry. This cooperation between space and time is remarkably smooth. There is no sudden threshold where distances abruptly collapse. The effect grows gradually as speed increases. At low speeds, it is too small to notice. At higher speeds, it becomes measurable. Near the cosmic limit, it dominates the behaviour of motion entirely. What makes this cooperation so elegant is that it does not require agreement between observers. Each observer measures distances and durations using their own clocks and rulers, and within their own reference frame, everything behaves normally. Objects feel solid, rulers remain straight, nothing appears distorted. The differences only emerge when measurements are compared across frames. This is why length contraction does not feel like being compressed from the inside. A traveller moving at high speed does not feel squashed. Their surroundings feel normal. It is only when someone in a different state of motion measures those surroundings that the difference appears. Once again, space-time preserves internal consistency while allowing external disagreement. This behaviour can feel counterintuitive because everyday experience suggests that space is absolute. But just as time revealed its flexibility when motion became extreme, space reveals that it too is responsive. Neither is rigid. Both adjust together to maintain a deeper structure. That deeper structure is space-time itself. Space-time is not space plus time. It is the framework that defines how distances and durations relate. Motion through space-time is shared between spatial movement and temporal progression. When one increases, the other adjusts. Length contraction and time dilation are simply two sides of the same coin. Light makes this especially clear. Because light always moves at the cosmic speed limit, space and time must always cooperate perfectly along its path. The distance light travels and the time it takes are locked together by that boundary. No observer can alter that relationship. Measurements of distance and time may differ, but their ratio remains fixed. This is why light is such a powerful probe of space-time. By observing how light travels, bends, and arrives, scientists learn how space and time are structured. Light traces the geometry exactly, revealing how distances stretch and shrink as motion and gravity come into play. For objects with mass, the story is similar but less extreme. As they approach the cosmic limit, space contracts more strongly along their direction of motion. This contraction does not destroy structure. It preserves it. By shortening distances, space-time prevents velocities from exceeding the boundary set by light. This preservation is not restrictive. It is stabilizing. If space did not contract at high speeds, then objects could cross the cosmic limit simply by accumulating enough energy. Distances would remain fixed while time slowed, and speed would continue to rise unchecked. By allowing space to adjust as well, space-time closes that loophole entirely. Once again, the universe avoids contradiction without drama. There is something quietly reassuring about this behaviour. No matter how fast something moves, space-time responds in a coordinated way, redistributing distance and duration so that the fundamental structure remains intact. Motion becomes extreme, but order survives. This cooperation also hints at why space and time are inseparable at a fundamental level. They are not independent dimensions that occasionally interact. They are aspects of a single system that respond together whenever motion demands it. At everyday speeds, this unity is hidden. At extreme speeds, it becomes unavoidable. Understanding this does not require abandoning intuition entirely. It requires extending it. Journeys still take time. Distances still matter. What changes is the realization that space and time negotiate with one another, sharing the burden of motion to keep reality consistent. The cosmic speed limit defined by the speed of light is not enforced by forbidding motion. It is enforced by cooperation. Space shortens. Time stretches. Paths remain viable. No observer gains a privileged perspective. Space joins the conversation not as a passive stage, but as an active participant. And in doing so, it reveals that motion is not just about where something goes, but about how space-time itself reshapes to allow that motion without breaking its own rules. Distance is no longer fixed, time is no longer absolute, and yet the universe remains remarkably stable. This stability is not accidental. It is the result of space and time working together, guided by a single boundary that keeps motion meaningful, measurements consistent, and reality shared, even as speeds approach the fastest pace the universe allows. Everything that moves does so within a framework it cannot step outside of. Objects travel, clocks tick, light propagates, particles collide. Yet none of this happens in empty isolation. All motion takes place within a deeper structure that gives meaning to distance, duration, and direction. That structure is space-time. Space-time is not a background laid out behind the universe like a painted backdrop. It is the stage and the script at the same time. It defines what counts as near or far, before or after, possible or impossible. Every event, from the birth of a star to the flicker of a photon, traces a path through this combined fabric of space and time. In everyday life, space-time feels invisible. Space feels like a container, and time like a clock ticking independently in the background. Motion feels like something objects do within that container. This separation works well at human scales because space-time is only gently curved and motion is slow compared to the cosmic limit. Under these conditions, the deeper structure stays politely out of view. At extreme speeds and energies, space-time stops being shy. When motion pushes toward the fastest pace the universe allows, space-time reveals itself not as a passive setting, but as an active organizer. It determines which paths exist, how distances are measured, how time flows, and how events connect. Nothing outruns it. Nothing escapes it. Everything obeys it automatically. Light offers the clearest illustration of this role. Light does not behave as though it is making choices. It does not decide how fast to go or which route to take. It simply follows the geometry laid out by space-time. Where space-time is flat, light travels in straight lines. Where space-time curves, light curves with it. Where space-time stretches, light stretches its wavelength. At no point does light consult its own preferences. This is because light does not carry the freedom that massive objects do. Objects with mass can choose different paths through space-time. They can move slowly or quickly, linger or rush, trade space for time in varying proportions. Their motion has flexibility because they are not locked to the boundary of what space-time allows. They exist inside the structure with room to maneuver. Light lives on the structure itself. Because light has no rest mass, it cannot step away from the paths defined by spacetime's geometry. It follows what physicists call the Null structure of spacetime, the set of paths that mark the absolute limit of how events can be connected. Along these paths, space and time are balanced so precisely that no proper time passes at all. This is not a dramatic statement. It is a geometric one. Light does not experience time passing, because there is no frame in which light can be said to experience anything. There is no rest frame, no internal clock, no perspective from which light could observe itself moving. Light simply connects events. It links causes to effects at the fastest rate space-time permits. Seen this way, light's speed is not something it possesses. It is something space-time enforces. This distinction matters because it removes any sense that light is special by exception. Light is not fast because it has extraordinary properties that break the rules. It is fast because it obeys the rules completely. It traces the deepest pathways space-time provides, revealing the structure by following it perfectly. Space-time in turn sets those pathways automatically. There is no separate instruction telling space-time how to behave. Its geometry emerges from how energy, momentum, and mass are distributed throughout the universe. That geometry then determines how objects move, how light travels, and how time flows. The rules are not applied after the fact. They are embedded from the start. This is why the cosmic speed limit feels so inevitable once space-time is understood. It is not an added constraint placed on motion. It is a boundary defined by the shape of space-time itself. Just as a curved surface limits which paths are shortest, space-time limits which connections are possible. Light follows the shortest paths available to it within this geometry, paths that preserve the universal pace at which information can travel. Massive objects follow longer, slower paths because they cannot fully align with those boundary routes. They always retain some motion through time, which keeps them inside the structure rather than on its edge. This also explains why light always moves at the same speed for all observers. If light were choosing its speed, then different observers moving relative to one another would measure different values. Instead, everyone measures the same pace because they are all observing the same geometric feature. The speed of light is not relative because spacetime is not relative in that way. Its structure is shared. Observers may disagree about distances and durations, but they agree about the boundary that links them. That boundary is what light traces. This agreement is not enforced by communication or convention. It arises naturally from the fact that all observers exist within the same spacetime. Their rulers and clocks may slice it differently, but they are slicing the same object. The geometry does not change from one observer to another. Only the coordinates do. This is why spacetime can be thought of as the silent referee of motion. It does not intervene. It does not react emotionally. It simply defines what paths exist. Objects move freely along those paths, unaware of the constraints because the constraints are identical to the possibilities. Nothing ever feels like it is being stopped. It simply moves as allowed. There is something deeply calming about this realization. The universe does not need constant correction to remain coherent. It does not rely on hidden forces to prevent contradictions. The structure itself ensures that motion, causality, and information remain ordered. Light plays its role not as a rebel but as a guide, tracing the edges of what spacetime permits. This perspective also reframes the idea of speed limits entirely. The cosmic speed limit is not about restricting motion. It is about defining connection. It tells the universe how quickly events can influence one another. It gives shape to cause and effect. It allows time to have an order without being rigid. Spacetime is what makes this possible. By linking space and time into a single fabric, spacetime creates a natural scale for motion. Light reveals that scale by living on it. Everything else navigates within it. No choice is required. No rulebook is consulted. The geometry does the work quietly and consistently. Once spacetime is understood as the stage everything moves through, light's behaviour stops feeling mysterious. It becomes a consequence. Light does not race. It does not accelerate. It does not slow. It simply follows the only kind of path available to something without mass in a universe where spacetime has a defined structure. That structure in turn uses light as its signature. The speed of light defines how space and time relate. It sets the conversion rate between distance and duration. It anchors the geometry so that all observers, no matter how they move, share a common framework. Without it, space-time would lose its coherence. With it, the universe remains intelligible. Space-time is not an abstract idea layered on top of physics. It is the reason physics holds together at all. Motion makes sense because space-time gives it meaning. Light behaves the way it does because space-time demands it. Nothing is choosing its speed. The universe is simply following its own shape. One of the strangest discoveries in physics is not that light is fast, but that it is stubbornly consistent. No matter who measures it, no matter how they are moving, no matter where they are in the universe, the measured speed of light always comes out the same. This is not approximately true, it is not true on average, it is exactly, relentlessly true. At first, this feels wrong. In everyday life, speeds add and subtract naturally. If you walk forward on a moving train, your speed relative to the ground increases. If you throw a ball from a moving car, the ball carries the car's motion with it. Velocities stack. Motion feels relative, flexible, negotiable. There is no reason, from daily experience alone, to expect any speed to remain fixed for all observers. And yet, light refuses to play along. If one observer is standing still and another is moving toward a beam of light, both measure that light travelling at the same speed. If one observer moves away from the source, and another moves toward it, both still measure the same value. Even if two observers are racing past each other at enormous speeds, each finds that light behaves identically. This consistency is deeply counterintuitive because it contradicts how every other speed behaves. The confusion comes from assuming that light's speed should behave like the speed of an object. A car's speed depends on the road. A plane's speed depends on the air. A thrown ball depends on the motion of the thrower. In all these cases, speed is relative because it is measured against a medium or a frame that can change. Light has no such medium. Light does not travel through space the way a sound wave travels through air, or a ripple moves across water. There is no background substance that carries it along. Light's motion is not measured relative to space as a thing. It is measured relative to space-time itself. This difference is subtle, but it changes everything. To see why, it helps to step back and consider how measurements are actually made. Measuring speed requires two ingredients: distance and time. An observer needs a ruler to measure how far something travels and a clock to measure how long it takes. If either the ruler or the clock behaves differently, the measured speed will change even if the motion itself does not. At everyday speeds, rulers and clocks agree closely enough that this complication stays hidden. Space feels rigid. Time feels universal. Different observers may move relative to one another, but their measurements remain nearly interchangeable. At extreme speeds, that agreement breaks down. When observers move relative to one another, they do not share the same definition of distance or the same definition of simultaneity. They slice space-time differently. What one observer considers here and now, another may consider slightly separated in time. These differences are tiny at low speeds and enormous at high speeds. This is where light's consistency enters as a stabilizing feature. Instead of allowing the speed of light to vary from observer to observer, space-time adjusts the measurements themselves. Time stretches, lengths contract, clocks tick at different rates, distances along the direction of motion shrink. All of these changes happen in exactly the right proportions to ensure that when distance is divided by time, the result for light is always the same. Light speed is preserved because space and time conspire to preserve it. An everyday analogy can help, even if it is imperfect. Imagine walking on a moving walkway at an airport. From your perspective, your walking pace feels normal. From the perspective of someone standing still beside the walkway, your overall motion is faster. Both descriptions are correct because the ground beneath you is moving. Now imagine a universe where the walkway itself adjusts its length, and the clocks measuring your steps adjust their timing depending on who is watching. No matter how anyone measures your motion, the ratio between steps and seconds always comes out the same. The walkway stretches or shrinks, the clocks speed up or slow down, but the measured pace remains fixed. This is closer to how light behaves. Light does not slow down or speed up to accommodate observers. Observers adjust unknowingly to accommodate light. Their measurements adapt because space-time adapts. The geometry does the work quietly without announcing itself. This is why it is misleading to say that observers see light behaving strangely. Light behaves consistently. It is everything else that bends around that consistency. The effect becomes easier to accept when reframed. Instead of asking why light always measures the same speed, it helps to ask what would happen if it did not. If light's speed depended on the observer's motion, then there would be a preferred frame of reference. One state of motion would be special. One observer would be able to say they were truly at rest while others were not. The universe does not allow this. All inertial observers are equivalent. No experiment performed entirely within a smoothly moving system can reveal its absolute motion. This principle would collapse if light behaved like an ordinary object. The consistency of light speed protects the symmetry of physical laws. It also protects causality. If light speed varied between observers, then the order of events could change unpredictably. Signals could arrive before they were sent in some frames. Effects could precede causes depending on who was watching. By locking light speed in place, spacetime ensures that cause and effect remain globally consistent, even when perspectives differ. This is why the speed of light is more than just a number. It is a structural constant. It defines how space and time convert into one another. It sets the maximum rate at which information can travel. It anchors the geometry so that all observers, no matter how they move, agree on the fundamental ordering of events. Once this is understood, the constancy of light speed stops feeling like a bizarre exception and starts feeling like a necessity. Light always measures the same speed because space-time is built that way. The universe has chosen consistency over convenience. Instead of allowing speeds to add freely, it allows space and time to flex. Instead of letting observers disagree about physical laws, it lets them disagree about measurements while preserving deeper agreement. This choice has consequences everywhere. It shapes how energy behaves at high speeds. It explains why massive objects cannot reach the cosmic limit. It determines how clocks tick on satellites and how particles behave in accelerators. It even plays a role in the chemistry that allows atoms to exist in stable forms. The calm beauty of this arrangement is easy to overlook because it works so well. Light never announces that it is following a rule. It simply does. The universe never pauses to enforce the rule. It is enforced automatically by the structure of space-time itself. What once felt like a contradiction becomes a cornerstone. Light always measures the same speed, not because observers are mistaken, and not because measurements are flawed, but because reality is organized around that fact. Space and time are not rigid containers. They are responsive partners that reshape themselves to keep that boundary intact. In this light, the question changes. It is no longer, how can light possibly behave this way? It becomes, how could the universe work at all if it did not? The consistency of light speed is not an inconvenience that physics must explain away. It is a clue to how deeply ordered the universe is beneath its surface complexity. It tells us that even when perspectives differ, there is a shared structure holding everything together. Light reveals that structure simply by being itself. It moves as space-time allows, at a pace space-time defines, and in doing so it quietly reminds every observer that while motion is relative, the rules that govern it are not. Motion feels obvious at first. Something moves or it does not. A car passes by. A cloud drifts overhead. A cup rests quietly on a table. It seems natural to divide the world into things that are moving and things that are still, as if stillness were a clear and universal state. That sense of clarity comes from everyday experience, where differences in motion are small and shared frames of reference are taken for granted. People on the same street, in the same room, on the same planet, tend to agree on what counts as rest. The ground beneath their feet feels solid and unmoving. Against that background, motion feels absolute. The universe does not share that assumption. When motion is examined carefully, especially at high precision or extreme speeds, the idea of absolute rest quietly disappears. There is no universal backdrop that defines what it means to be truly still. Motion only ever exists in relation to something else. An object is moving relative to one observer and at rest relative to another, and both descriptions can be equally valid. This is not a philosophical statement. It is a physical one. Consider a simple example. A passenger sitting in a train may feel perfectly still. Their coffee does not slide across the table. Their body does not strain against motion. Yet to someone standing on the platform, that same passenger is moving rapidly down the track. Neither perspective is wrong. Motion depends on viewpoint. This relativity of motion extends far beyond trains and platforms. The Earth rotates, it orbits the Sun moves through the galaxy drifts within a larger cosmic structure. At no point does there appear a special frame that can be labelled truly at rest. Every candidate turns out to be moving relative to something else. This realization unsettles intuition because it removes a comforting anchor. If there is no absolute rest, then motion has no universal reference point. Speed becomes something measured between observers rather than something an object possesses on its own. At low speeds, this subtlety barely matters. Differences between reference frames are small, and everyday measurements agree closely enough that the illusion of absoluteness holds. At high speeds, the illusion collapses completely. This is where light fits into the picture so naturally. Light does not single out a preferred frame of reference. It does not behave differently depending on who is watching. Its speed remains the same for all observers, regardless of how they move. This property only makes sense in a universe where motion itself is not absolute. If there were a universal state of rest, light could be measured relative to it. Observers moving toward or away from that state would see different speeds. The fact that this never happens tells us something profound. There is no privileged frame hiding beneath appearances. Instead, all inertial observers are treated equally by the laws of physics. This equality explains why speed comparisons behave so strangely at high velocities. When two objects move toward each other, their speeds do not simply add the way intuition expects. When one object chases another near the cosmic speed limit, the gap between them closes more slowly than classical reasoning predicts. These outcomes feel counterintuitive because they violate the idea of absolute motion. The universe is not malfunctioning, it is revealing its structure. Speed comparisons rely on measurements of distance and time, and those measurements depend on the observer's state of motion. As observers move differently, their clocks tick at different rates, and their rulers measure different lengths along the direction of motion. When these effects are taken into account, speed comparisons stop behaving linearly. This does not mean that motion becomes arbitrary, it becomes relational. Every observer measures motion using their own clocks and rulers, all governed by the same spacetime geometry. Each description is internally consistent. Disagreements only appear when measurements are compared across frames. Those disagreements are not contradictions. They are features of a universe without absolute rest. Light's role here is especially revealing. Because light always moves at the same speed for all observers, it cannot be used to define a state of rest. There is no experiment involving light alone that can reveal how fast an observer is moving in some absolute sense. This protects the principle that no inertial frame is special. Light fits perfectly into this framework because it lives at the boundary space-time defines. It does not move relative to space as an object moves relative to a road. It traces the structure itself. Asking whether light is moving absolutely misses the point. Light's motion defines the relationship between space and time, rather than occurring within a pre-existing space. This reframing helps explain why attempts to find absolute motion always fail. No matter how carefully experiments are designed, they always yield the same result. Motion can be measured relative to other objects, but not relative to spacetime itself in a way that singles out a universal rest frame. This is not a limitation of instruments, it is a property of reality. The absence of absolute motion also preserves the consistency of physical laws. If one frame was special, then the laws of physics could behave differently depending on motion. Certain experiments would work only when performed at rest. Others would fail when repeated in motion. The universe avoids this complexity by treating all inertial frames equally. This equality is not enforced externally. It emerges from space-time structure. When motion is relative, comparisons must account for how measurements change with speed. This leads to results that feel strange at first but remain deeply orderly. time dilation and length contraction are not oddities layered on top of physics. They are the natural consequences of removing absolute rest from the picture. Speed comparisons behave strangely because intuition expects a fixed background that does not exist. Once that expectation is released, the behaviour becomes easier to accept. Two observers moving relative to one another are not disagreeing about reality itself. They are describing the same events using different coordinate systems shaped by their motion. Both descriptions are valid within their own frames. Light anchors these descriptions by providing a shared boundary. Its speed remains the same for all observers, ensuring that even without absolute rest, there is a universal structure everyone agrees on. This shared structure allows observers to translate between perspectives without contradiction. In this sense, light does not break the relativity of motion, it completes it. Without a universal state of rest, motion becomes a relationship rather than a property. Without light's consistent speed, that relationship would dissolve into confusion. Together, they create a universe that is flexible without being chaotic, relative without being arbitrary. There is something quietly elegant about this arrangement. Nothing needs to be pinned down absolutely for the universe to function. Order emerges from relationships rather than fixed points. Motion remains meaningful even without a universal reference. This elegance also explains why the question, "How fast am I really moving?" has no absolute answer. One can always ask, relative to what? The answer depends on the chosen frame, and no frame has priority over another. Light respects this fully. It offers no shortcut to absolute motion. It treats all observers the same, reinforcing the idea that motion itself has no privileged baseline. Once this is understood, the strange behaviour of speed comparisons becomes less troubling. It is not that the universe is hiding something, it is that it never offered an absolute reference point in the first place. Motion is not absolute. It is contextual, relational, and woven into spacetime itself. Light moves as spacetime allows. Objects move within that allowance. Observers describe motion from where they are, using the tools available to them. The absence of absolute rest is not a deficiency. It is a design feature that keeps the universe coherent, symmetrical, and fair to all observers. And within that design, light plays its role perfectly, not by standing still or moving absolutely, but by revealing the structure that makes all motion possible. Being at rest feels like the simplest state imaginable. A book lying on a table is at rest. A parked car is at rest. Sitting quietly, breathing slowly, nothing about the experience suggests motion at all. Rest feels like the absence of movement, the baseline from which all motion begins. That feeling comes from habit, not from physics. To say something is at rest is always to leave part of the sentence unfinished. At rest relative to what? Relative to the table, relative to the road, relative to the earth. The moment that question is asked, rest becomes conditional rather than absolute. What appears motionless in one frame can be moving rapidly in another. A person sitting in a chair is at rest relative to the room, yet they are rotating with the Earth, orbiting the Sun, and moving with the galaxy. None of these motions are felt because they are shared with the surroundings. Rest, then, is not the absence of motion, but motion that is matched by everything nearby. This idea works cleanly for objects with mass. Any object with mass can always find a reference frame in which it is at rest. No matter how fast it is moving relative to someone else, it is always possible to move alongside it, match its motion, and declare it stationary. In that frame, the object has no spatial velocity. It occupies a fixed position. Time passes. Clocks tick. The object experiences duration. This ability to define a rest frame is deeply tied to what mass is. Massive objects move through spacetime in a way that always includes a component through time. Even when spatial motion is removed by changing reference frames, motion through time remains. This gives massive objects internal histories. They age, they can carry clocks, they can remember where they have been. Light cannot do this. There is no reference frame in which light is at rest. This is not a technological limitation or a gap in experimental ingenuity. It is a consequence of how spacetime is structured. Attempting to imagine a frame that moves alongside light leads immediately to contradictions. The very act of defining such a frame would require spacetime to behave in a way it simply does not allow. If one tries to chase a beam of light and match its motion, something strange happens. No matter how fast the observer moves, light still pulls away at the same pace. There is no remaining gap to close, no final adjustment that brings the observer into alignment. The target keeps receding, not because light accelerates, but because spacetime refuses to provide a frame where light stands still. This refusal is absolute. The reason lies in how motion through spacetime is divided between space and time. Objects with mass always move partly through time and partly through space. By adjusting reference frames, observers can redistribute that motion, reducing spatial speed while increasing temporal progression, or vice versa. But the total motion through spacetime never changes. Light sits at a limit where this redistribution is no longer possible. For light, all motion is directed through space. There is no leftover motion available for time. Along the path of light, no proper time passes. From emission to absorption, light does not experience an interval, it does not age, it does not linger, it connects events directly. This is not something light perceives, because perception requires time. It is a statement about geometry. Because light has no rest mass, it cannot slow down without ceasing to be light. Slowing would require diverting some of its motion into time, but there is no capacity for that. The structure of spacetime does not offer light any alternative paths. The only available routes are those that move at the cosmic speed limit. This is why light has no rest frame by definition. It is not that light refuses to rest. It is that rest does not exist for light as a concept. There is no coordinate system in which light occupies a fixed spatial position while time passes. The mathematics of spacetime simply does not permit it, and neither does experiment. This makes light unique, but not arbitrary. Light is unique because it lives on the boundary of spacetime's geometry. It traces the fastest possible connections between events. Everything else moves inside that boundary. Objects with mass can approach it, but they can never reach it. Light is born there. This also explains why light speed is locked in place. If light could slow down, then it would have a rest frame. If it could speed up, then it would exceed the boundary spacetime defines. Neither option exists. The speed of light is not selected from a range. It is fixed because spacetime only allows one kind of motion for massless entities. This locking is not enforced dynamically. There is no force acting on light to keep it moving at that speed. There is no resistance to overcome. Light simply follows the only paths that exist for it. Once again, geometry does the work. The idea of a rest frame is closely tied to the idea of carrying a clock. A rest frame allows an object to define its own time, to mark moments passing internally. Massive objects can do this. They can say, "Time passed for me while I stayed here." Light cannot say this because there is no internal time for light. This difference is profound but often misunderstood. It is tempting to imagine what light experiences as it travels, but that question has no physical meaning. Experience requires a frame, and light has none. Any attempt to describe light's perspective immediately collapses into contradiction, because perspective itself is defined by time passing within a frame. Light is not an observer, it is a connector. This helps explain why light plays such a central role in physics. It defines the structure of spacetime not by measuring it, but by following it exactly. Where spacetime curves, light curves. Where spacetime stretches, light's wavelength stretches. Light reveals geometry without distortion, because it has no inertia, no rest frame, and no internal clock to complicate the picture. The absence of a rest frame also protects the consistency of physics. If light had a rest frame, that frame would be special. It would define absolute motion. Observers could measure their speed relative to light at rest, and discover whether they were truly moving or not. The symmetry of physical laws would collapse. Certain frames would become privileged. The universe avoids this by making light unreastable. Because light cannot be at rest, no observer can ever claim to be at rest relative to the ultimate structure of spacetime. Motion remains relational. All inertial frames are treated equally. The laws of physics behave the same way in all of them. This is not a coincidence. It is a requirement for a coherent universe. Light's lack of a rest frame is not an oddity layered on top of physics. It is one of the pillars holding everything together. It ensures that speed comparisons remain meaningful, without absolute reference points. It guarantees that causality remains intact. It anchors the geometry so that space and time relate consistently for all observers. What makes this especially elegant is how quietly it all works. Nothing about everyday life hints at this structure. Light fills rooms, reflects off surfaces, warms skin, and carries images without announcing its deeper role. Yet beneath these ordinary interactions lies a strict geometric rule that shapes the universe at every scale. Light does not pause, it does not hesitate, it does not negotiate its speed. It moves as spacetime allows, and spacetime allows exactly one option. This is why light always behaves the way it does, no matter who measures it or how they move. The absence of a rest frame locks its speed in place not as a constraint but as a definition. To be light is to move at that pace. Anything else would not be light at all. Understanding this reframes the original mystery. Light is not fast because it is special. It is special because it occupies the boundary where motion, time, and space converge. It does not break the rules of the universe. It reveals them. And in doing so, it reminds us that rest, motion, and speed are not absolute facts written into objects, but relationships shaped by space-time itself. Light simply shows what those relationships look like when taken to their most extreme, precise, and unavoidable conclusion. Cause and effect feel so fundamental that they are rarely questioned. A sound follows a knock. A light turns on after a switch is flipped. Rain wets the ground, not the other way around. Events unfold in a clear order, and that order gives the world a sense of reliability. Things happen, then other things respond. This sense of order feels natural because it is woven into experience from the very beginning. In everyday life, causes come before effects, and the gap between them feels smooth and predictable. Even when delays occur, the sequence remains intact. The expectation is not just that events happen, but that they happen in the right order. This expectation is what physicists call causality. Causality is the principle that effects do not precede their causes, and that information flows forward through time rather than backward. It is not merely a habit of thought. It is a structural feature of how the universe operates. Without it, explanation itself would fall apart. The cosmic speed limit plays a quiet but essential role in protecting this structure. Because there is a maximum rate at which information can travel, there is also a maximum rate at which causes can influence effects. Signals propagate outward. Influences spread gradually. Events connect in layers rather than collapsing into simultaneity. The universe unfolds in an orderly way because it cannot update itself instantaneously. This limit ensures that nearby events can influence one another before distant ones do. It gives time a direction. It allows sequences to exist rather than everything happening all at once. At low speeds, this role is invisible. Signals travel so quickly compared to human experience that cause and effect feel immediate. Flip a switch, and the light responds. Speak, and the sound reaches nearby ears almost instantly. The underlying delays are present but too small to notice. At extreme speeds, the importance of the limit becomes impossible to ignore. If objects or information could travel faster than the cosmic speed limit, the ordering of events would become unstable. Different observers, moving relative to one another, could disagree not just about how long things took, but about which event happened first. In some frames, an effect could appear to occur before its cause. This is not speculation. It follows directly from how spacetime relates time and distance. When speeds remain below the cosmic limit, spacetime preserves a consistent ordering of events. All observers agree on which events can influence which others. They may disagree about durations or distances, but they agree about causal relationships. No observer ever sees a signal arrive before it was sent. If faster-than-light motion were allowed, that agreement would break. An influence travelling faster than the cosmic limit would move outside the light cones that define causal structure. It could connect events in ways that reverse their temporal order in some frames. A message could be sent, received, and responded to before it was transmitted, depending on the observer's motion. This would not create dramatic paradoxes in the everyday sense. The universe would not collapse or explode. Instead, it would lose coherence. Cause and effect would become frame-dependent. Explanation would lose its footing. The notion of prediction would weaken because outcomes could no longer be reliably traced back to prior conditions. The cosmic speed limit prevents this quietly and completely. By ensuring that no information travels faster than light, spacetime guarantees that causal order is preserved for all observers. Effects always remain within the future light cone of their causes. No frame sees influence travelling backward in time. This protection does not require intervention. It is automatic. Light defines the boundary of causal connection. Anything that can influence something else must do so at or below that pace. Forces, signals, interactions, and changes all respect this limit, not because they are forced to, but because spacetime does not offer paths that violate it. This is why the speed of light is sometimes described as the speed of causality rather than the speed of illumination. Light itself is just one form of information. The deeper rule applies to all meaningful influence. This perspective helps clarify why faster-than-light ideas feel tempting, but ultimately fail. At first glance, allowing faster signals seems like it would simply make communication more efficient. Messages would arrive sooner, distances would feel smaller, the universe might feel more connected. What is easy to miss is that speed is not just about convenience, it is about structure. Once the limit is broken, structure unravels. The universe avoids this not by banning speed, but by shaping space-time so that such motion cannot exist. There are no hidden exceptions, no loopholes waiting to be discovered. Even phenomena that seem instantaneous, such as certain quantum correlations, turn out not to transmit usable information faster than light. This consistency is not fragile. It has been tested repeatedly across scales, from subatomic interactions to astronomical observations. Every confirmed experiment respects the same causal boundary. There is something reassuring about this reliability. The universe does not rely on delicate balancing acts to preserve order. It builds that order into its geometry. Cause and effect are protected not by rules layered on top of reality, but by the shape of reality itself. This also explains why the cosmic speed limit feels less like a restriction and more like a stabilizer. Without it, time would lose its direction. Prediction would lose its meaning. Events would blur together in ways that defy explanation. With it, the universe remains navigable. Stories can unfold, processes can complete, information can travel without chaos. Even at extreme speeds, this stability holds. Objects approach the cosmic limit and experience time dilation and length contraction. Measurements change, perspectives diverge. Yet causality remains intact. No observer ever sees an effect outrun its cause. No signal ever arrives before it is sent. Light sits precisely at the edge of this structure. By moving at the maximum allowed pace, light traces the boundary of what can influence what. It defines the horizon beyond which events cannot be connected. Everything slower remains safely inside that horizon. Everything meaningful respects it. This role gives light a quiet authority. It is not just fast, it is foundational. The calm elegance of this arrangement often goes unnoticed because it works so well. Cause and effect feel natural because space-time enforces them relentlessly. The universe does not need constant correction to stay sensible. It is sensible by design. Understanding this reframes the idea of limits entirely. The cosmic speed limit is not a constraint that holds reality back. It is a framework that holds reality together. It allows complexity without contradiction. It permits change without chaos. It gives time an arrow without making it rigid. Nothing is being prevented for arbitrary reasons. The universe is preserving its own coherence. When imagined this way, the question of faster-than-light motion loses its appeal. It is not that such motion is forbidden by stubborn laws. It is that allowing it would dissolve the structure that makes laws meaningful in the first place. Causality survives because the cosmic speed limit exists. Order survives because influence spreads at a finite pace. The universe remains understandable because effects follow causes in all frames without exception. Light does not merely illuminate the world, it outlines the boundaries within which the world can function, and by doing so, it quietly ensures that reality unfolds as a sequence rather than a tangle, stable enough to be explored, predicted, and understood without ever breaking its own sense of time. When people hear about the cosmic speed limit, it is natural to picture beams of light racing through space. Light is vivid and familiar, so it becomes the symbol of the limit itself. But the rule reaches far beyond illumination. It does not belong to light alone. It applies to information, influence, and cause in all their forms. This distinction matters, because information is what actually connects events. Information is any physical change that can be used to distinguish one state from another. A flicker on a screen, a vibration in the air, a particle collision, a chemical reaction. Whenever something happens, and that happening can, in principle, affect something else, information is involved. Light is simply one of the most efficient carriers of it. The cosmic speed limit governs how fast that influence can spread. At first, this can feel abstract because information often feels intangible. But information is always tied to physical processes. It must be carried by something, whether that something is a wave, a particle, or a field interacting with space-time. There is no such thing as information without a physical footprint. Because of that, information cannot outrun the structure of space-time itself. This is why the speed limit matters far beyond light beams crossing the void. It applies equally to radio signals, gravitational influences, electrical interactions, and any process by which one event can affect another. All of these respect the same boundary, even when their mechanisms differ. At everyday scales, this is easy to forget. Messages feel instantaneous. A tap on a screen triggers a response. A voice is heard almost as soon as it is spoken. The delays are real, but they are so small compared to human perception that they fade into the background. Cause and effect appear immediate, reinforcing the illusion that information can travel without constraint. At larger scales, the reality becomes clearer. Signals sent across planets take minutes to arrive. Communications between stars take years. Light from distant galaxies carries information that is millions or billions of years old. The universe does not update itself all at once. It unfolds gradually, with information spreading outward at a finite pace. This gradual spread is not an inconvenience. It is a necessity. If information could travel infinitely fast, then all events would be connected instantly. Distance would lose meaning. Locality would vanish. Every part of the universe would respond to every other part immediately. The result would not be efficiency. It would be incoherence. By limiting how fast information can propagate, spacetime preserves structure. Signals remain local before becoming global. Causes influence nearby effects before distant ones. Complex systems can evolve without being overwhelmed by instant feedback from everywhere else. The universe remains layered rather than flat. This layering is what allows processes to have duration. Consider something as simple as conversation. Words leave one mouth, travel through air, and arrive at another set of ears. Meaning unfolds over time. Even thought itself relies on ordered signals travelling between neurons. If information moved infinitely fast, there would be no sequence, only simultaneity. Experience itself would lose its rhythm. The cosmic speed limit protects that rhythm. Light happens to travel at the maximum rate allowed by spacetime, which makes it a convenient reference. But it is not the rule. It is the messenger that reveals the rule. Information carried by any other means can never arrive sooner than light could have arrived along the same path. This is why the speed of light is sometimes described as the speed of information. Not because information must be light, but because light traces the boundary of what information is allowed to do. Anything that attempts to move influence faster would be attempting to move outside spacetime structure, and spacetime does not permit that. This connection between information and causality is crucial. A cause is only meaningful if its effect follows it. Information is what links the two. If information could outrun the cosmic speed limit, then effects could appear disconnected from causes, or even precede them in some frames. By enforcing a universal boundary, spacetime ensures that causal chains remain intact. This applies even in situations that seem to challenge the rule. Quantum phenomena, for example, often give the impression of instant connection. Measurements performed on entangled particles show correlations that appear immediately, regardless of distance. It is tempting to think that information is being transmitted instantaneously in these cases, but it is not. While the correlations are real, no usable information travels faster than light. No message can be sent. No influence can be controlled. The outcomes only make sense when results are later compared using signals that respect the cosmic speed limit. The structure of causality remains untouched. This distinction highlights an important point. Not all correlations involve information transfer. Two events can be linked by a shared history without one sending a signal to the other. Information, in the sense that matters for causality, requires the ability to influence outcomes. That influence is always bounded. The universe is careful about this. It allows subtle connections without allowing violations of order. It permits patterns without permitting paradoxes. The speed limit applies not to coincidence, but to control. This is why nothing meaningful can outrun light. Particles may fluctuate. Fields may extend. Mathematical descriptions may suggest instant relationships. But any change that can be used to affect something else, to send a message, or to trigger a response must respect the same finite pace. Meaning travels slowly enough for order to survive. This has profound consequences across physics. It determines how forces act. It shapes how stars form and collapse. It governs how energy moves through matter. It even influences the stability of atoms, where electromagnetic interactions propagate at the cosmic limit rather than acting instantly. Without this constraint, matter itself would behave differently. Atoms rely on delayed interactions to maintain structure. Chemical bonds depend on signals that take time to propagate. Life depends on sequences of cause and effect unfolding in a reliable order. The speed limit is woven into the fabric of existence, from the smallest scales to the largest. Seen this way, the rule feels less like a barrier and more like an agreement. Spacetime agrees to let information flow, but not all at once. It agrees to let events influence one another, but not without delay. It allows complexity to grow by preventing everything from happening everywhere simultaneously. There is a quiet generosity in this. The universe does not rush itself. It unfolds at a pace that preserves meaning. Information arrives when it arrives, shaped by distance, motion, and geometry. No observer is overwhelmed by infinite immediacy. No system is destabilized by instant feedback. Light in this context becomes a guide rather than a limit. It shows how fast information can travel without breaking causality. It traces the fastest allowable connections. Everything else moves within that boundary, slower but still meaningful. This also reframes how technology is understood. Faster communication always feels desirable, but even the most advanced systems must respect the same rule. Improvements come from efficiency, encoding, and processing, not from outrunning spacetime itself. The cosmic speed limit is not a challenge to overcome, it is a foundation to build upon. Once this is recognized, the focus shifts. Instead of asking how to send information faster than light, the more meaningful questions become how to use information wisely within the structure that exists, how to synchronize, predict, and understand within a universe that values order over immediacy. Information moves at the pace spacetime allows. Cause follows effect in a sequence spacetime protects. Nothing meaningful outruns light because meaning itself depends on the delay. In that delay, the universe finds its rhythm. Events connect without collapsing. Influence spreads without confusion. Reality unfolds as a story rather than a snapshot. Light does not merely illuminate that story, it defines the speed at which the story can be told. Gravity is often imagined as a force that pulls things inward, drawing objects together across space. Apples fall, planets orbit, stars gather matter from their surroundings. This picture works well for many purposes, but it hides a deeper truth about how gravity actually operates, especially when it comes to light and the cosmic speed limit. Gravity does not reach out and tug on objects from a distance. It reshapes space-time itself. When mass and energy are present, space-time curves. Distances change. Time flows differently. Paths that once seemed straight gently bend. Objects moving through this curved structure simply follow the available routes, much like a marble rolling across a curved surface. Nothing is being grabbed or dragged. Motion unfolds naturally within the geometry that gravity creates. Light is no exception to this. Because light has no mass, it does not feel gravity as a pull in the usual sense, and yet light responds profoundly to gravity. When light passes near a massive object, its path bends. When light climbs out of a gravitational well, its frequency shifts. When light travels through regions where gravity is strong, time itself flows differently along its path. These effects can feel paradoxical at first. How can something without mass be influenced by gravity? The answer is that gravity does not act on mass alone. It acts on space-time, and light, which lives entirely within space-time, must follow wherever that structure leads. Imagine space-time as a landscape whose shape is determined by mass and energy. Where there is little mass, the landscape is nearly flat. Where there is great mass, the landscape curves deeply. Objects move by following the natural contours of this terrain. Light, having no inertia, traces those contours with perfect fidelity. This is why light bends near stars and galaxies. The bending is not dramatic in most situations. Near the Sun, for example, the effect is small but measurable. Starlight passing close to the Sun appears slightly shifted from its usual position in the sky. This bending was first observed during a solar eclipse in 1919, providing early confirmation that gravity affects light by curving space-time rather than pulling directly. In stronger gravitational fields, the effect becomes more pronounced. Near massive galaxies or clusters of galaxies, light can bend so much that it produces arcs, rings, and multiple images of the same distant object. These phenomena, known as gravitational lensing, allow astronomers to map the distribution of mass in the universe, including mass that cannot be seen directly. Gravity also affects the timing of light. When light travels through a region of strong gravity, time passes more slowly relative to regions with weaker gravity. This means that light takes longer to traverse a gravitational well than it would if space were flat. From the perspective of a distant observer, light appears to slow down as it passes near massive objects. This phrasing can be misleading if taken too literally. Locally, light always moves at the cosmic speed limit. An observer falling alongside the light in a gravitational field still measures it travelling at the same speed. The apparent slowing occurs when measurements are compared across regions with different gravitational strengths. Time itself is flowing differently in those regions, and that difference shows up in how long light appears to take. Once again, space-time does the work. Gravity stretches time and warps space in such a way that light's behaviour changes without ever violating the cosmic speed limit. Light never exceeds that limit, and it never drops below it locally. The adjustments happen through geometry, not through changes in light's intrinsic motion. This distinction is crucial. It might seem tempting to imagine gravity overpowering the speed limit, dragging light along slower paths or trapping it entirely, but gravity does not override the limit. It works within it. Even in the most extreme environments, the fundamental rule remains intact. Black holes offer a dramatic illustration. Near a black hole, space-time curves so strongly that all available paths point inward. Light emitted too close to the event horizon cannot escape, not because it slows down, but because every possible future direction leads deeper into the gravitational well. The speed limit is respected perfectly. What changes is the shape of space-time itself. From far away, light emitted near a black hole appears increasingly redshifted and delayed, as if it were struggling to climb out. Clocks near the horizon tick more and more slowly relative to distant observers. Yet locally, nothing special happens. Light still moves at the same pace. Time still flows normally for nearby observers. Gravity has not broken the rule, it has reshaped the stage. This reshaping reinforces the universality of the cosmic speed limit. No matter how strong gravity becomes, no matter how extreme the curvature of space-time, the same boundary governs motion and information. Light always traces the fastest possible paths allowed by the geometry, and those paths never exceed the defined limit. This universality is deeply reassuring. It means that the same principles apply everywhere, near stars, between galaxies, at the edge of black holes. The universe does not switch rules in extreme environments. It uses the same framework, stretched and curved but never replaced. There is a quiet elegance in how gravity and the speed limit coexist. Gravity influences how space and time are arranged. The speed limit governs how motion unfolds within that arrangement. Neither dominates the other. They're aspects of the same structure, working together to keep reality coherent. This partnership also explains why gravity feels so different from other interactions. Forces like electromagnetism act within space-time, pushing and pulling objects along its surface. Gravity shapes space-time itself, changing the rules of distance and duration that all other processes rely on. Light responds to this shaping instantly, not because it is fast, but because it has no inertia to resist. Where spacetime curves, light curves. Where time stretches, light's frequency shifts. Where paths narrow, light follows the narrowing. This responsiveness makes light an extraordinary tool for understanding gravity. By watching how light bends, stretches, and delays, scientists can infer the shape of spacetime itself. Light becomes a tracer, revealing invisible structures through its motion. Yet even here, nothing breaks the cosmic rule. The same speed limit that governs motion in empty space governs motion near the most massive objects in the universe. Gravity adds complexity, but not contradiction. It deepens the story without rewriting it. There is something calming about this consistency. No matter how exotic the environment, the universe remains understandable. The same principle apply everywhere. Space and time cooperate. Light obeys geometry. Information respects causality. The framework holds. Gravity does not threaten the speed limit. It showcases it. By bending light without slowing it, by delaying signals without reversing order, by trapping paths without violating pace, gravity demonstrates how flexible and robust spacetime truly is. It can curve dramatically and still preserve the same fundamental boundaries. This balance allows the universe to be both dynamic and stable. Stars can form and collapse. Galaxies can merge and distort spacetime on vast scales. Light can travel across billions of years and arrive carrying coherent information. None of this would be possible if gravity and the speed limit were in conflict. Instead, they are partners. Together they shape a universe that is rich without being chaotic, curved without being broken, and complex without losing its underlying order. Light moves as spacetime allows. Gravity shapes what spacetime allows. The speed limit remains quietly in place, not as a restriction, but as a foundation. In that foundation lies a profound sense of unity. Whether light is skimming past a star, threading its way through a galaxy, or hovering at the edge of a black hole, the same rule applies. Motion remains meaningful. Information remains ordered. Reality remains whole. Gravity bends the path, but the pace endures. And in that endurance, the universe reveals not rigidity, but a deep, calming consistency that holds everything together, no matter how extreme the journey becomes. Quantum physics has a reputation for breaking rules, bending logic and quietly undoing everything that felt solid before. Words like strange and weird are used so often that it can feel as though the quantum world lives by an entirely different set of laws, one where distance does not matter and limits quietly dissolve. When the topic is the speed of light, this reputation naturally raises a concern. If anything were going to slip past the cosmic speed limit, surely it would be something quantum. It does not. Despite its unfamiliar behaviour, quantum physics respects the same boundary that governs stars, planets, and light itself. The speed limit remains intact, not as a fragile rule that must be defended, but as a deep structural feature that quantum theory is built around from the beginning. The confusion comes not from what quantum physics allows, but from how its ideas are often described. At very small scales, particles are not treated as tiny objects with fixed positions and paths. Instead, they are described by spread-out possibilities, patterns that assign probabilities rather than certainties. Until a measurement is made, outcomes are not settled in advance. This probabilistic language can make it seem as though reality itself is vague or undecided, as if events are happening everywhere at once. It is easy to mistake this uncertainty for freedom from limits. Uncertainty, however, is not speed. Quantum systems can be unpredictable without being unconstrained. The way outcomes are chosen may be probabilistic, but the way information moves through spacetime remains tightly regulated. No quantum effect allows controllable influence to appear somewhere else faster than light could have travelled between those locations. The structure that preserves causality at large scales remains fully active at small ones. The most persistent misunderstanding appears with quantum entanglement. Entangled particles share a link description, meaning that certain properties are correlated no matter how far apart the particles are separated. Measure one particle, and the outcome for the other becomes immediately defined, even if the distance between them is vast. The word immediately is where trouble begins, because it invites the image of something racing across space faster than light. Nothing races anywhere. What exists is a shared state created earlier, when the particles interacted or were produced together. That shared description contains correlations that only become apparent when measurements are compared. The act of measuring one particle does not send a signal to the other. It does not carry a message, a command, or an influence. It simply reveals one part of a pattern that was already there. A familiar analogy helps, even if it is imperfect. Imagine separating a pair of gloves and placing them in sealed boxes. Open one box and discover a left glove, and the nature of the other glove is instantly known. No information travelled between the boxes at the moment of opening. The correlation existed from the start. Quantum entanglement works on a deeper level than gloves, but the logic is the same. Correlation is not communication. This distinction matters because information is what carries causal power. To send information, there must be a way to choose an outcome and have that choice affect something else. Quantum measurements do not allow this. The results are fundamentally random. One cannot decide in advance which outcome will occur, and therefore cannot encode a message in the result. Without control, there is no signal. Only later, when results from both locations are brought together using ordinary communication that respects the cosmic speed limit, do the correlations become visible. Until that comparison happens, nothing useful has travelled faster than light. The speed limit remains untouched, doing its quiet work in the background. Quantum tunnelling often raises similar concerns. In tunnelling, particles sometimes appear on the other side of a barrier they do not have enough energy to cross. The mathematical descriptions can suggest extremely short durations or ambiguous timing, leading to claims that tunnelling involves faster than light motion. Here again, interpretation matters. Tunnelling does not involve a particle sprinting through space at impossible speeds. It reflects the way quantum possibilities extend into regions that classical motion forbids. The particle does not follow a well-defined path through the barrier, and no usable signal can be sent using tunnelling effects. When experiments are designed to test causality directly, the results always respect the same limits found everywhere else in physics. This consistency is not accidental. Modern quantum theory is built to coexist with relativity. Quantum field theory, which underpins particle physics, enforces locality at a fundamental level. Interactions occur at specific points in spacetime. Influences propagate outward. Mathematical terms that would allow faster-than-light communication cancel out or are forbidden entirely. The theory does not merely tolerate the speed limit, it depends on it. This dependence reflects a deeper truth. Any theory that allows information to outrun spacetime quickly collapses into contradiction. Causes lose their place. Predictions lose their meaning. The versions of quantum theory that survived experimental testing are the ones that preserve causal order, even while abandoning classical certainty. What often feels strange about quantum physics is not that it breaks structure, but that it reshapes expectations. It replaces determinism with probability. It softens the idea that outcomes must be fixed in advance. Yet beneath that softness lies a firm framework. Events still unfold in sequence. Influence still spreads at a finite pace. space and time still matter. Even the most exotic quantum effects turn out to be deeply local when examined carefully. Interactions occur where fields overlap. Correlations arise from shared histories. Nothing meaningful leaps across space instantaneously. The universe remains layered, not collapsed into a single moment. There is a quiet reassurance in this. The universe does not fracture into incompatible rule sets as scales change. The same principles apply to atoms and galaxies alike. Quantum behaviour adds texture and depth, not loopholes. It enriches the story without rewriting the ending. Quantum light illustrates this beautifully. Treated quantum mechanically, light arrives in discrete packets, interferes with itself, and exhibits uncertainty. Yet when it comes to speed, it behaves exactly as before. It traces the same boundary defined by spacetime. It carries information at the same maximum pace. The rule does not bend simply because the description has changed. This continuity explains why attempts to use quantum effects for faster-than-light communication always fail. Clever setups can reveal astonishing correlations, but the moment one tries to turn those correlations into messages, the structure closes in, randomness blocks control, locality blocks influence, causality holds. The universe seems remarkably uninterested in shortcuts. Instead of allowing information to rush everywhere at once, it insists on sequence. Instead of collapsing distance, it preserves it. Instead of letting quantum weirdness unravel order, it integrates it seamlessly into the same framework that governs everything else. Quantum physics does not weaken the cosmic speed limit. It reinforces it by showing how deeply it is embedded. Even where intuition struggles most, the rule remains steady. Information moves at the pace spacetime allows. Causes precede effects. Structure survives uncertainty. The same old rule holds, not because reality lacks imagination, but because coherence requires it. Quantum behaviour may change how outcomes are chosen, but it does not change how they spread. Light, whether classical or quantum, still follows the same geometry. Influence still respects the same boundary. In the end, quantum mechanics does not undermine the calm story being told. It confirms it. No matter how strange the details become, the foundation remains solid. The universe allows mystery, probability, and surprise, but it does so within a structure that never lets meaning outrun itself. The cosmic speed limit can feel abstract when it's discussed in terms of light beams, space-time, and distant galaxies, but its influence reaches far deeper than those grand images suggest. It quietly shapes everything that exists, from the life cycle of stars to the stability of atoms, from the chemistry of living cells to the rhythm of everyday experience. This limit is not a distant rule operating only at the edges of the universe. It is woven into the texture of reality at every scale. Consider stars first, because stars are where much of the universe's structure begins. Inside a star, immense pressures and temperatures drive nuclear reactions that release vast amounts of energy. That energy does not appear everywhere at once. It moves outward gradually, carried by photons and particles that scatter, interact, and transfer influence step by step. The speed limit governs how quickly those interactions can occur, shaping how stars balance gravity against radiation. Without that limit, energy would rush outward instantaneously, and stars would not settle into stable lifetimes measured in millions or billions of years. They would burn violently and briefly or fail to shine at all. The same rule determines how stars die. When massive stars collapse or explode, the information about that collapse spreads outward at a finite pace. Shock waves propagate. Neutrinos escape. Light follows behind. The structure of supernovae, neutron stars, and black holes all depends on the fact that influence moves stepwise rather than instantly. The universe is allowed to respond to change, but never all at once. Move down in scale, and the same limit continues its quiet work. Atoms exist because electromagnetic interactions do not act instantaneously. Electrons respond to the presence of nuclei through fields that propagate at the cosmic speed limit. The stability of electron orbits, the formation of chemical bonds, and the predictability of atomic spectra all depend on interactions unfolding over time rather than collapsing into immediate response. If information travelled infinitely fast, atomic structure would change dramatically, likely becoming unstable or unrecognizable. Chemistry, which builds on atomic behaviour, inherits this structure. Chemical reactions proceed through sequences of interactions, not instantaneous rearrangements. Bonds stretch, vibrate, and break according to signals that propagate at finite speed. The speed limit ensures that reactions have duration, direction, and order, allowing complex molecules to form rather than dissolving into chaos. Life depends on this ordering more than anything else. Inside living cells, signals move through chemical gradients, electrical impulses, and molecular interactions. Nerves fire, muscles contract, hormones circulate. Each process unfolds in time, shaped by delays that are small but essential. If information moved without limit, biological systems would lose their timing, feedback loops would collapse, coordination would vanish. Life would not simply speed up, it would fail. Even perception relies on the speed limit. Light takes time to reach eyes. Sound takes time to reach ears. Nerves take time to carry signals to the brain. The sense of now is constructed from these delays, blended into a coherent experience. The world feels stable because information arrives in an orderly way, not because it arrives instantly. Remove the cosmic speed limit and everyday reality becomes unrecognizable. Distance would lose meaning. Local events would instantly affect distant ones. Causes and effects would blur together. Systems that rely on gradual change would be overwhelmed by immediate feedback. The universe would not feel more efficient. It would feel fragile, unstable, and incoherent. The speed limit prevents that outcome by imposing a gentle discipline on reality. It ensures that influence spreads outward rather than exploding everywhere at once. It allows systems to respond, adjust, and settle. It creates room for processes to unfold rather than collapse into simultaneity. In doing so, it makes complexity possible. This discipline is not harsh. It does not feel restrictive in daily life because it operates far beyond the scales humans usually notice. Yet its presence can be felt in the very fact that daily life has rhythm. Conversations take time, journeys have duration, growth and decay follow patterns. Nothing meaningful happens all at once. There is a quiet beauty in this. The universe does not rush itself. It allows events to breathe. Stars shine long enough for planets to form. Planets orbit long enough for chemistry to deepen. Chemistry persists long enough for life to emerge. Life unfolds long enough to ask questions about the universe that made it possible. The cosmic speed limit underwrites all of this without drawing attention to itself. It does not announce its role. It simply ensures that change remains manageable. Even at the most extreme scales where time stretches and space bends, the same rule applies. The universe remains consistent with itself, never abandoning the structure that allows it to exist at all. This consistency extends into the most familiar moments. Waiting for a message, watching a sunrise, feeling a heartbeat. Each experience is shaped by delays that are small but essential. The speed limit gives those delays meaning. It turns sequence into story. There's no need to marvel loudly at this. Quiet appreciation fits better. The rule is not dramatic. It does not seek attention. It does not feel like a barrier. It feels like a background presence, holding everything together while remaining unseen. Like gravity, it reveals itself only when imagined absent. Without it, reality would be louder, harsher, and far less forgiving. With it, the universe becomes navigable. Causes lead to effects. Systems remain stable. Complexity grows rather than collapses. Time acquires direction without becoming rigid. Space retains meaning without becoming isolating. This speed is not just a number, it is a scaffold. It shapes how matter organizes, how energy flows, how information spreads, and how experience unfolds. It gives the universe permission to be intricate without being chaotic. It allows change without confusion. As this idea settles, the focus naturally shifts away from limits and towards structure. The speed of light is not interesting because it is fast. It is interesting because it sets the tempo of reality itself. Everything dances to that tempo, whether noticed or not. There is something calming in realizing this. The universe is not balanced on a knife edge. It is supported by deep, steady principles that operate everywhere, all the time. The same rule that governs distant galaxies quietly governs the chemistry of breath and the firing of thoughts. Nothing needs to hurry. Everything moves at the pace that allows meaning to exist. And in that shared pace, stars, atoms, life, and thought find room to unfold, one moment at a time. It is easy to frame the story of light as one of limitation. Why can it not go faster? What is holding it back? What invisible barrier does it keep running into? Framed this way, the speed of light can feel like an arbitrary ceiling, a frustrating boundary placed on something that otherwise seems free. But this framing quietly misses the point. Light is not slow, and it is not restrained. It is moving exactly as reality allows. To understand this, the idea of speed itself needs to soften. Speed usually means how quickly something moves through space over time, like a car on a road or a runner on a track. In those situations, space and time sit quietly in the background while motion plays out within them. Light does not move within space and time in that way. It moves along the structure formed by space and time together. Its speed is not measured against a backdrop. It is woven into the backdrop itself. Light is not failing to go faster. It is already doing the maximum that space-time permits. When light travels, it is not choosing a speed from a range of options. It is following the only kind of path available to something without rest mass. Massive objects can trade motion through space for motion through time. They can slow down spatially and speed up temporally, or vice versa. Light has no such freedom. It moves entirely along the boundary where space and time meet, with no option to tilt that motion one way or another. That boundary has a fixed slope, and light follows it perfectly. This is why asking why light does not slow down or speed up misses something fundamental. For light, motion is not adjustable, it is defined. The speed associated with light is not a property of light itself in the way mass or charge might be. It is a property of space-time. It reflects how distances and durations relate to one another at the deepest level. Change that speed, and space and time would have to change with it. Reality would need to be rebuilt from the ground up. This reframing turns the original question inside out. Instead of asking why light is limited, it becomes more accurate to ask why reality has the structure it does. Why does space-time have the geometry that gives rise to this particular pace? Why do space and time combine in a way that produces this boundary at all? The answer is not that something went wrong. It is that this structure works. A universe where light moved faster or slower would not simply be a scaled version of this one. It would be fundamentally different. Cause and effect would behave differently. Atoms would bind differently. Stars would live and die differently. Information would spread at a different rhythm. The universe would not just feel unfamiliar, it would likely be unstable or incoherent. In this sense, the speed of light is not a constraint imposed on an otherwise flexible reality. It is a defining feature that makes reality possible in its current form. Light moves at the pace that preserves order. This is why the speed limit has appeared again and again throughout the story, not as an obstacle, but as a stabilizer. It protects causality. It preserves sequence. It allows complexity to emerge without collapsing into simultaneity. It gives the universe time to respond to itself. When light traces this boundary, it reveals space-time rather than fighting it. It shows how space stretches, how time flows, and how motion must behave to keep everything consistent. Light is not bumping into a wall, it is outlining the shape of the room. Seen this way, there is nothing frustrating about light's speed. There is something deeply elegant about it. Light is not slow compared to some imaginary faster alternative. It is as fast as meaning allows. It is as fast as information can travel without undoing the order that makes information useful in the first place. It is as fast as cause and effect can propagate while remaining in the right order for all observers. Anything faster would not be an improvement. It would be a breakdown. This realization gently resolves the mystery that started the journey. The question was never really about light. It was about why reality behaves the way it does. Light simply sits at the edge of that behavior, making the structure visible. Massive objects slow down as they approach this edge because they are not meant to reach it. Their motion is divided between space and time, and pushing further requires reshaping time itself. Light, having no mass, lives entirely on that edge from the beginning. It does not accelerate toward it. It begins there. That is why light has no rest frame. That is why its speed is the same for everyone. That is why adding energy does not make it go faster. These are not quirks. They are consequences of definition. Light is not a traveller choosing a route, it is the route. There is a quiet calm in recognizing this. The universe is not enforcing arbitrary speed limits like a cosmic traffic officer. It is expressing its own geometry. Space and time are arranged in a particular way, and light faithfully follows that arrangement. Nothing is being denied. Everything is behaving as it must. This perspective also softens the human instinct to push against limits. It replaces the idea of restriction with the idea of structure. The speed of light is not something to overcome, it is something to understand. It tells a story about how reality holds together. That story is remarkably consistent. From the smallest quantum interactions to the largest cosmic structures, the same pace applies. The same boundary shapes motion, information, and influence everywhere. The universe does not switch gears. It does not contradict itself. It keeps the same rhythm throughout. Light moves at that rhythm because it defines it. When this settles in, the original frustration dissolves. There is no sense of something being held back. There is instead a sense of things fitting together. Space, time, motion, and information all align around the same principle. The universe feels less like a collection of rules and more like a coherent whole. Light is not slow, it is precise. It moves at exactly the speed that allows reality to exist as something ordered, stable, and knowable. It does not rush, it does not lag, it does not need to. It arrives exactly where it should, when it should, tracing the structure that makes everything else possible. And in that steady motion, the universe finds its balance, unfolding calmly, moment by moment, without ever needing to hurry. The question that began this journey sounded simple at first. If light has no mass, why does it have a speed limit? Along the way, that question quietly changed shape. It stopped being about light as an object and became a question about the structure of reality itself. Light was never being held back. It was showing how space and time are woven together. The speed associated with light does not come from light struggling against some invisible resistance. It comes from space-time defining how distance and duration relate to one another. Light moves at that pace because it traces the deepest geometry of the universe. It follows the natural contours of space and time exactly as they are, not faster and not slower. What first looked like a limitation turns out to be a definition. Seen this way, the universe feels less restrictive and more thoughtfully arranged. The same rule appears everywhere, shaping stars, atoms, signals, gravity, and even the flow of cause and effect. Nothing special has to be added to make it work. The consistency is built in. No matter the scale, the same quiet structure holds. There is something calming in that realization. Reality is not patched together from exceptions and loopholes. It does not rely on fragile balances or hidden tricks. It rests on a small number of deep principles that apply gently but firmly everywhere at once. The speed of light is one of those principles, not because it is dramatic, but because it is dependable. Light moves exactly as reality allows, because reality allows exactly that much motion. In doing so, it preserves order, sequence, and meaning, without ever announcing its role. It simply does what it has always done, tracing the framework that makes everything else possible. As this thought settles, the need to push further fades. There is no mystery left to chase, only a structure to appreciate. The universe is not rushing. It is unfolding at a pace that makes sense. Light keeps that pace faithfully, and in doing so keeps everything else gently in place. There's nothing more to solve, only something steady to rest with.